Okay, so let's take a look at a couple of examples here, and we'll work through those, and then we will also take a little time here toward the end and do the quiz. Okay, a couple things we're going to look at. First off, how do you go about determining either an increasing or a decreasing exponential function? Easy enough to tell if it's increasing or decreasing. If the numbers get bigger, the thing is increasing. If the numbers get smaller, the thing is decreasing. That's easy enough. Second thing, we've already talked some about this. If you have a function and the base, the b value, the number that's associated with the x and the exponent, okay? If that number is between 0 and 1, it's decaying. If that b value is bigger than 1, it's growing. Okay? So if you have 0 is less than b is less than 1, what you have there is a decay. If you have b is greater than 1, what you have there is growth. There are two values that are oftentimes of interest with exponential growth and decay. The one is, how long does it take for something to double? The other is, how long does it take for it to cut in half? With regard to doubling, if you're investing, the question is, how long is it going to take for this money that has been put into whatever account, how long is it going to take for it to double in value? In the case of something like a car or a drug concentration in your bloodstream, antibiotics, whatever it might be, how long is it going to take before it is half of what it started at? Okay? We've been kind of looking around, debating, should we buy a new truck? Okay? We're buying one that's pretty much stripped down but diesel. How much does a stripped down diesel truck cost anymore? Okay? If careful, you can buy one at $50. This is no leather seats. This is just plain old rubber floors, cloth seats. It doesn't even have on the dashboard the GPS or any of that stuff. I mean, this is stripped down. $50,000. Put in the GPS, the leather, carpet, all that stuff that's going to get ruined around cattle and manure, and you're talking $70,000 and $80,000 for a pickup truck. Did you know that? The catch is, if we decide to buy one of those, what's going to happen to our $50,000 purchase? It's going to go down in value, isn't it? We're going to be losing money. And the thing I'm really asking is, can we keep the truck that we've got going longer, or is it time to lose $50,000? When you buy a car, you're going to lose that money. Okay? So, please? Well, part of the catch on our truck is the frame is starting to rust through, etc., etc. How much does a diesel engine cost? About 15 grand. Okay? And that's without the stuff to adapt it to the transmission, because you probably can't find the exact same engine, blah, blah, blah. So you're looking at between $15,000 and $20,000 just to drop another engine in. The engine runs fine. The engine's beautiful. It's not the engine that's the problem, it's the chassis. Okay, let's take a look at an example here of something that's growing exponentially. You all know about Spotify, right? Company started in Stockholm, still based in Stockholm. It's been around for about 8 years now. Okay? Here are some numbers of active users on Spotify. 2012 is right here. And these other numbers are years since 2012. So this down here would be what year? 2017. 2017. This is the number of active users on Spotify, people who use it on a regular basis. If you take a look at that number of users, is that growing linearly or in some other way? Okay. If you want, one way to determine if it's going linear or not is to look at the change at each step. This is an increase of 9, 16, 35. This is growth of 25. This is a growth of 40. If the growth at each step is basically the same amount, so if you looked at it, it was 3, 3, 3, 3, 3, or pretty close to 3, that would be an example of linear. In this case, other than the 25 there, it's going 9, 16, 35, 40. Okay? At first it grows pretty quickly, and then it, of course, continues to grow here some, but not so quickly. The growth is looking something like that, isn't it? If you were to graph the 9, the 16, the 35, the 25 is kind of a hiccup, the 40. If you were to graph those numbers, wouldn't those numbers kind of do something like that? That's not linear growth, that is exponential. Now, with something like this, the question would be, well, how are we going to figure out how growth is actually taking place? And one of the things that you can do is you create ratios. Ooh, we've talked about ratios already. So for example, you first create a ratio with the number of people using it in 2013 compared to 2012. So I'm going to copy down the numbers up here on the board quick like. Those numbers are 15, 24, 40, 75, 100, and 140, and this is going to be your 0, 1, 2, 3, 4, and 5. Okay, so we have those numbers that we're going to be working with. In the first box on the table, we're going to do a ratio of 2013 to 2012. Well, in 2013, there were 24 million users. 2012, 15 million. You can take that, plug that in on your calculator, and do the 24 divided by the 15. It's about 1.6. On the next box, we're going to do 2014 versus 2013. Well, that's going to be the 40 over the 24. So if we do the 40 divided by the 24, it's going to be 1.67. If we go with the next one, that's going to be the 75 over the 40. Do you see how this works? Okay, so I do the 75 divided by the 40, and that's about 1.86. Now the next one, we're going the 75 to the 100, so that's going to be the 100 over the 75. And if you do the 100 divided by the 75, you get 1.33. And then in the last one, what we're going to do is the 140 over the 100. And if you do the 140 divided by the 100, you're going to get 1.4. Now, because this is actual data, is it going to perfectly match a pattern? The answer is no, it's not going to be perfect, because out in the real world, nothing's perfect. Okay. However, what do you notice about those values? What's kind of like an average value there for those? Would you buy it? Well, it's between 1.3 and 1.8, isn't it? those out. So if we took the 1.6 plus 1.67 plus 1.86 plus 1.33 plus 1.4 equals, and we're going to divide by what? 5, yeah. 7.86 divided by 5 equals. If you average it out, you get that it's about 1.572. There's the average. Does that make sense what we've done so far? Well, what's that 1.572 going to represent? I'm going to write this down so I don't forget it. 1.572 is what we got. Okay. This 1.572 is going to be this growth factor. It's the B value, and it's bigger than 1, isn't it? So it's going to be a growth factor in this case. And is it going to be a perfect growth factor? The answer is no. It's just going to sort of kind of match it. But when you're working with real data, you just kind of sort of do the best you can do. Okay? We can use that information to create our own equation for how that data is growing. What we can do, notice we came up with 1.572 something or other. What they've done here is they've rounded it off to 1.58. Okay, they've used a little more data, but what they wind up with is about the same as what we got, isn't it, for that ratio. That ratio shows you how things are increasing. That ratio is what you're going to use for your B value. And the question then is, well, gosh, the equation for exponential functions is A times B to the x. Well, we know what B equals. We'll call it 1.58. Okay? In this example, we're going to have this value A times the 1.58 to the x power. Now we have to figure out what A is. A is another number. A is actually pretty straightforward to figure out. If we start with x equals 0, see it? That's our 2012 data. If we start with x equals 0, we can plug that information in, and we're going to get A times 1.58 to the 0 power equals, and what number should come out when we plug 0 in? When we plug 0 in, we should get 15 out. That's exactly right. Does that make sense to everybody? So we take this equation and we set it equal to 15. Ooh, Chuck, I've never had to solve anything like this before. And actually, it's pretty straightforward to solve because 1.58 to the 0 power equals what? 1. Any number raised to the 0 power is 1. Okay? So what this really gives us is A times 1 equals 15. Well, what's that mean A is going to equal? Yeah, 15. So our equation can then be written as y equals 15 times 1.58 to the x power. And you have a model now to try and describe the number of users over some period of years. And remember, it's a model. Is it perfect? No. It's just trying to describe what's going on and do a pretty good job of describing it. Okay? To complete this table would not be horrible. For example, in year 2, the model would be 15 times 1.58 squared. And we could work that out on a calculator. 15 times 1.58 squared equals, and here you get 37.45. That's at t equals 2. Now we can check our actual data. The model says it should be about 37.5 million users. Did that come close to year 2? Let's see, year 2 was 40 million, 37.5. That's not too far off. That's not awful. Okay. If we do year 3, that's going to be the 15 times the 1.58 cubed. So we're going to do 15 times 1.58 to the third power. And we come up there with 59.16. For year 3, is that sort of close? Or, it's off a little bit, isn't it? It's off kind of a chunk because they're at 75, isn't it? So it's off a piece there. This is a bit low from what actually happened. Okay. 15 times 1.58 to the fourth. Let's see how that works. 15 times 1.58 to the fourth equals 93 million. It's actually 93.48. Now, if you take a look at the 93.48 versus the original, or the actual data, is that pretty close? Yeah, that's not bad. That's pretty close. The 37 was pretty close. Okay, this was pretty close. The last data comes up is 147.7, and the actual number was 140. Once again, it's close. This one's a little bit high. And the others were all low, weren't they? Okay. So our model is starting out growing a little too slowly, and then it starts growing a little bit too fast. It's kind of like Goldilocks and the Three Bears. Some are a little too small, some are a little too big. You get that idea. Okay, does that make sense how this works? Very important thing to pick up on the previous slide here, where we did these ratios. Does that make sense on how you can use data to get your value for B? Getting that value for B is very important. Now, will this value for B always be bigger than 1? The answer is no. What if we're dealing with something like the depreciation on a car? Then the value for B would have a range of 0 to 1, wouldn't it? Does that make sense to everybody? So remember, this value for B might be bigger than 1, and if it's bigger than 1, that means things are growing. It might be between 0 and 1, and if it's between 0 and 1, that means things are decaying or decreasing. And that's completely legit. And when you walk up to a set of data and you're told this is, whatever it might be, the value of your couch, would you expect that to be an increasing or a decreasing function? Decreasing, right? The second you buy it and they bring it into your house, it is now a used couch. Would you get anywhere near what you paid for it? No. If you put it on Marketplace or eBay or wherever you're going to sell this thing, Craigslist, you aren't going to get anywhere near the $1,500 that you laid out for it. Okay. Yes.
So the B value is the average of the ratio.
Right. The B value is the average of the ratios. So you want to take your data, and for each pairing of data where you have two pieces of data, one right next to each other, you form a ratio of the more recent divided by the less recent. more recent divided by the less recent. In other words, the newer value divided by the older value. And those ratios won't always come out exactly the same, but they'll be sort of close. You can then take an average of those to figure out about what the B value should come up with. Then the model is A times B to the X. We've learned how to figure out the B value by doing those ratios. To get the A value, you just take and plug in one of your points, one of your data points. Could we have used 1 and 24? Yeah, that would have looked like A times 1.58 to the first power equals 24. And if you take the 24 then and you divide it by the 1.58, you get 15.18. This would give us an A value of 15.1, well, let's say 19. Is that pretty close to the A value we got over there? It is. Realize that if you use different points in the data, the value for A will come out different, but it should be pretty close. Now, this may be a surprise to you, but when you actually get into mathematics and you actually get into working with real world stuff, there is no one right answer. That only occurs in arithmetic and algebra. The only place you get one right answer is in arithmetic and algebra. As you move along in math, the answer is somewhere in this range. Because as you move along in math, most of the time you're working with something out in the real world, right? And what out there exactly follows any rule? Nothing. So you won't be able to mathematically find a rule that everything perfectly follows. That may be news to you. That may be one of the first times you've ever been told that in math, answers usually come in a range. There is no one perfect right answer. Ever heard that one before in a math class? Okay. How about that? So there's something new for you today. And very honestly, that's how the world really works. Hey, do you remember on last week's quiz where I asked you about buying whatever, what was it, a washing machine? Yeah, a washing machine. And I asked you, should you buy this washing machine or not? And when you got your papers back, if you said, no, I'm going to go with the less expensive one because, and it was a good reason, that was full credit. If you said, yes, I'm going to buy the more efficient one because, and it was a legit reason, that was full credit. You could make the case either direction. But which is the right answer, Chuck? It depends what you value more. It depends how long you want to wait to get your money back. For different people, there are different right answers. What car should I buy? Should I buy a Honda Civic? Should I buy a dually diesel Dodge? Should I buy a Maserati? Those are all the right answer to some version of that question, aren't they? The next question might be, what do you want to do with it? Well, I just want to drive it up and down the road and get really good mileage. Well, which one of those would be the correct answer to that? The Civic. I want to be able to pull 40 and 50,000 pounds. Okay, not quite that much. 35,000 pounds. Cummins. I want to be able to do 185. Maserati. Yeah, somebody recognized, a couple of you probably recognized it. Okay, does that make sense? Let's take a couple minutes here, go after this quiz.